All right. So we'll talk about 3.4 and hopefully 3.5 today. And we'll talk by giving some more definitions on how sets work. So set operations. So first we need to know the definition of a universal set. This is not a place where TV shows get made down in Los Angeles. It's basically the set of everything that could make up a set. So the book says it contains all, and I cannot write and talk at the same time. Contains all elements from which sets are created. And so that seems super broad because it is super broad. Um, so either our brains break and is like, this set contains absolutely everything in the universe, or what you'll see in the textbook is it has like, here's all the list of numbers I want you to consider. So it could be truly universal, or it could just be, here's the things to consider for this specific problem. And so the book writes it as omega. Sometimes you'll also see like the letter U, capital U, to represent the universal set. The book uses omega, so that's what I'll use. And so in one of the problems later, we'll say like omega is the set of numbers where x is in the natural numbers such that x is between 1 and 10. And so I would like you to think, like, if we list out all the elements of the universal set, what is that? Because it seems super complicated, but we can just list them. Turn to your neighbor. What is this set? How can we write it more simply? Natural numbers. Yeah, so it looks complicated, but it's really not. So remember, this is natural numbers, which starts at 1, 2, 3, goes on to infinity. And so this is equal to, so this is the more general clause, and then the right-hand side is the more specific clause. So we're not looking at every natural number. We can't write all of those down, but we've put a bound on it to say it's between 1 and 10. So we can say that this set is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This seems like a good question that I would put on the exam. So make sure that you understand like these symbols of what do they mean? Integers, natural numbers, real numbers, and then understand how this sort of set works. So we've got the more general thing and then the more specific thing. All right, that's the universal set. We can say that the complement of a set, and so let's say if we say complement of some set A, and the caveat that it's of course relative to what's in our universal set, because if I said I want to consider the set of everything but my mug of tea, then that would be like literally everything else in the universe. Or if it's relative to the object that I have out on this table, then it would be like the book, computer, the iPad, stuff like that. So it's relative to whatever universal set we're working with. And so the complement of A is denoted A with a bar over it. And I believe it's overline, but don't quote me on that in LaTeX. So the complement of A, we denote A with a bar over it. And that basically means anything but the stuff that's in A. And so we write that as the complement of A is equal to the set of, more general statement, of all things in the universe, but not the stuff in A. Say, except the stuff in A. Note that it's not like it's not a complement with an I, it's complement with an E. So complement with an E means everything except the thing in this set. Complement with an I means that they're really nice to each other. All right, the union of, and so this is an operation that takes two sets. It's a binary operation of A and B. We denote with this big U looking thing. It is not the letter U. It is instead in LaTeX \cup. So it doesn't have the little tail that a capital U has. It's just a U with no tail. And so so the union of two sets is a set itself. And this is a set that has all the stuff in A and all the stuff in B. Let's be precise here. So it's the set of all elements in A or all elements in B or both. And so we'll see Venn diagrams a little bit later, but sometimes it's easy to understand with Venn diagrams. So let's say we have A and B, and so maybe they're completely separate over here. And so A union B is I'm going to take all the stuff in A, I'm going to take all the stuff in B. If there's some overlap, then A union B is all the stuff in A plus all the stuff in B plus all the stuff that both of them share. So A union B of these complementary sets is all the stuff in A, which is 1, 2, and 3, and all the stuff in B, which is 1 and 2. And so the union is just 1, 2, and 3, which just so happens to be A in the first place. And so we write this in set builder notation as A union B is equal to the set of all things X such that X is in A or X is in B. So whether it's in A or B, it's included. And remember, since if it's in both, remember T or T, like true or true is true. And so that is, now that we know the logic, that's how we get the or both category. All right, that's union, intersection. is, so again, this is a binary operation. So we write this with it's like the union symbol, but flipped upside down. This is cap. Did I say that was cup? Yes, I did. So we have cup, like the thing that holds water, and then we have cap, like the thing you put on your water bottle. So it's just flipped upside down. And this is the set of things that appear only in both A and B. So something that appears only in A but not in B won't be included. In our Venn diagram, we say that if this is A and this is B, then the intersection is the things in both of them. So it's that middle part. This is A and this is B. There's no overlap, and so there's no intersection. And so we say that these are disjoint. If there's no intersection, or we can also say that the intersection is empty. And so we can say that A intersect B is the empty set because there's no crossover. All right, in set builder notation, we say the intersection is A intersect B equals the set of all elements X such that X is in A and X is in B. So here's where we start to blend this is why we talked about logic and ands and ors and nots before we talked about the set operations. Okay, and so we talked about disjoint. All right, so now I've got an example for you. And I can go back if you need me to. So when the universal set is all the natural numbers such that X is between 1 and 10, we're going to say A is 2, 3, 5, 7, 9. B is 1 and 6. And C is 5, 6, and 9. I would like to know, what is C intersect B? What is C complement? And what is A union B intersect with A union C? All right, once you're done writing that down, turn to your neighbor and talk about it. All right, what's C intersect B? 6? And so how do I write that in set notation? So I know the answer is 6. Yeah. And so this is the set containing 6. What about C complement? Yeah. 1, 2, 3, 4, 7, 10.
Oh, and 8.
Order doesn't matter in a set. We're good.
Yeah.
All right, and then to make it in set notation, we just add the curly braces around that. And then what's this complicated thing? So this is so how to approach it is this is long and complicated, but there's parentheses. So let's work left to right and look inside the parentheses. So what's A union B? Yeah.
One, two, three.
Mm-hmm. And then what's A union C? Well, I think it's just A with a 6 in it. So 2, 3, 5, 6, 7, 9. And so then so now we've got this, now we've got that. Now we just intersect those two sets. And so set operations are a binary operation. So we only do it with 2 at a time. And so we do this 2 first and then this 2 second. So that way we're not doing 4 all at once. And so now that we've got 2 sets, we can intersect. Let's see. I think just this one, that's got a 1. The other doesn't have a 1. And so the intersection is just A union C, 2, 3, 5, 6, 7, 9. All right, great job. Okay. Any questions on that? Great. All right, more. Let's see. I want to show you this table. Let's see, that's over here. And it's on page 45. And so we got to scroll a little bit. This is it. So the book also shows a membership table, which I just want to show you that it's also possible where we can say that like, is X in A, is X in B? And this is just like a truth table where we can say X is in A, true or false. And then once we have that, then we can write the more complicated properties of X is in the complement of A, or X is in the union of A, or X is in the intersection of A and B. And so we can write it in that sort of format too. And so the next term is set difference. So this is again a binary operation. And so with 2 sets, we denote it with a slash, a backslash. Sometimes you'll see a minus B, but the more mathy way of putting it is the first one. When we get to LaTeX, you will find that the backslash character is special, where it enables all of the other things. So like, if I've been telling you that the union is backslash cup, then how do you actually type the backslash character? And so if you type backslash and then set minus, or if you just want like a normal backslash when you're typing, you can say text back slash. So that's how we write that character in LaTeX. And so so if we were looking at the difference of A and B, A minus B, then what we're going to get is all things in A that aren't also in B. So in Venn diagram land, this is A and this is B. We want all the things in A, but we don't want the things that are also in B. I just erased the actual diagram. So we choose all the stuff that's in A that's not also in B. And we write that in set builder notation as A set minus B is equal to everything in the universe such that X is in A and X is not in B. I think there's another way we could write it. We could say everything in A such that X is not in B. I think that's another equivalent way to write it. So this is the thing of there's multiple answers, multiple ways to get there, but as long as it's clear what you mean, then you'll be okay. So there's a lot of leeway. Yeah, question. Yes, I wrote that and then was like, oh, that's supposed to be an A. Then added the crossbar. Thank you. Okay, so that's minus. The product of two sets as long as they're not empty, is all ordered pairs from A and B, respectively. So A, and this is backslash times B is equal to the set of all ordered pairs.
We got something from my last class. Can I check real quick?
Oh yeah, sure, go for it. And so all ordered pairs we write as in parentheses A comma B. This is familiar from algebra where you have X comma Y such that, where'd it go? Lowercase a is in A and the lowercase b is in B. And so let's say if A is 1, 2, 3, and B is 4 and 5, then A product B is the set of 1 comma 4, 1 comma 5, 2 comma 4, 2 comma 5, 3 comma 4, and 3 comma 5. Thrilling stuff, I know. But it's ordered. And so you have the thing with A first and the thing with B second. And so this is that product. And so you don't have the case of like 4 comma 2. That's not part of this product because we said A times B. So A comes first. So only the things in A. It's probably called the product because, so let's see. What's the size of A? The cardinality of A? What's the cardinality of B? What's the cardinality of A times B? So if we multiply 3 by 2, we get 6. So that's probably where it got its name. And something you might, have you seen something like this before? Where we have like the real numbers squared? So if you take further math classes, chances are you'll see this. Where if we have like A times A, we use what we learned from algebra and say that's A squared. The real numbers squared just happens to be the Cartesian plane, right? X and Y. So There's real numbers on the x-axis, there's real numbers on the y-axis. So if we call that x and we call that y, then we mark a point as x comma y. So we've been doing that this whole time. All right, am I good to move on? Okay. The power set of a set. So this is a unary operation, so only on one set. And the power set of A, we denote by some fancy P. I think it's math SCR. And then you give it a letter. And then you say, here's the rest of that. So you make the fancy P with math SCR. Don't exactly quote me on that, but I think that's where that comes from. And so power set of A, we denote it with this fancy P, is just all the subsets. So remember, we have sets and then we have subsets. So if A is, let's start easy, just 1 and 2, then 1 is a subset of A, just 2 is a subset of A. Is 1 comma 2 a subset of A? Yeah, it just so happens to be equal, but that's allowed. Is the empty set a subset of A?
Yes.
Yes. So secretly in here, there's nothing. We just don't write it. So, and so so these happen to be all the subsets of A. And so now that we know all of them, we can say the power set of A is the set containing 1, because this is a set of sets. So the power set is a set of all subsets of A. And so the power set is the set containing 1, the set containing 2, the set containing 1 comma 2, which just so happens to be A itself, and the empty set. What's the cardinality of the power set? 4. What's the cardinality of A? 2. Okay, so it's a multiple. So I would like you to find, so let's say that C is equal to 5, 6, and 9. I would like to know what's the power set of C. And I would also like to know, so this example has A as 2, 3, 5, 7, and 9, and B as 1 and 6. What is A set minus C intersected with B set minus C? All right, talk about it. I think you should write it out because I'm going to ask you how big it is. And then if you finish that, then tell me what the power set of the set containing 1, 2, 3, and 4 is.
You did the second one. Two times. You're saying for that, the long one? Yeah, I'll give that. I'm still doing it. That's it. More the fact that there's zero survey versus just parentheses. Is this
Okay.
similar to what we should have?
For the second one?
Yes. This is like all of A that's not in C. Oh, we have five. And then all of B that's not in C. But it doesn't really intersect at all.
Right, so all in A that's not in C, that's correct. All in B that's not in C,
Or no, together. It's one.
just one.
Just the number one.
And so then,
And is where it intersects, I guess. I keep saying that. And not making sense.
well, it's like and is, like, logical and helps us define the notion of intersection.
There's zero intersection, so.
Yeah, so there's
Is it
no
just
cross.
empty set?
Yeah, so they're disjoint, so you can say disjoint or you can write the empty set.
That's not a P, that's just. You write the empty set, so the zero, that's not correct.
Like the fancy P? I don't know, it's, I guess, of cursive. But if you also just write like a capital P, then I'll probably know what you mean. The idea is that it looks a little bit fancy. All right, what's the power set of C? I think I agree with you for just this once. I'm gonna write with parentheses instead. What's the power set of C? Just yell sets at me. And I'm guessing 9. 5 and 6. 6 and 9. 5 and 9. 5, 6, and 9. And the empty set. And what's the size of the power set of C? What's the size of C? 3. Okay, so we've got, all right, I won't ask you to tell me what the power set of 4, 1, 2, 3, and 4 is, but would anyone like to tell me what's the cardinality of that set? If you worked it all out?
Yes.
Guess 15? So 14?
Probably right. I didn't work it all out. I guess.
Okay, so let's try and determine like how big's the power set. If you already know this number, then great. But let's try and figure it out as if we didn't know it. So if A contains only one element, what's the side of the power set? 2. Okay. What if A has nothing?
One.
Right, because the power set of an empty set, the power set is just going to be the empty set. Exactly. Um, if we have 2 things in our set, what's the side of the power set? We did this example. We have 3 things in our set. We found that the side of the power set was 8. And 4, $16 is correct. Can anyone guess what the formula is? If you don't, wait, so who knows what the formula is? Cool. Does anyone who doesn't know what the formula is want to take a guess? Yeah. Yeah. Wait, say that again. Yeah. So it ends up being the size of our set, 2 raised to the power of the size of our set. So if the size of our set is n, then the power set is size of our power set is 2 to the n. And this is just the set of all subsets. So this is something to keep in mind as you go forward of if you're trying to think through like, oh, what's all the possible like combinations I could have or something like this. Kind of get to be wary when you're looking at, oh, I'm actually looking at all of the subsets because this number, because it's the power of 2, can get fairly big fairly quickly. So just keep that in mind. This feels like something I might put on the exam. I haven't written the exam yet, but I'm starting to get vibes of the questions that will be there. All right. Some other things that I want to tell you super quickly. Has anyone not seen like the sigma notation for something? Where like if I have some number and I want to add all the things from 1 to 5, this is secretly 1 plus 2 plus 3 plus 4 plus 5. So the way that these sort of operators work is the sigma is basically a for loop that goes from I to n of something. And so this is saying for I to n. And then if we have some result that we define, then we say result plus equals whatever that is going over, what's going on over here, that goes on over here. So it's basically just a for loop. Something else you'll probably see notation wise is this So this is capital S sigma. This is a capital P pi. There's also a lowercase s sigma and a lowercase p pi, which is just the normal pi that you've used in geometry. So this is capital P pi. And so pi is just for products. Sigma for sum, pi for products. And so pi up to n of something is the same kind of thing. Result equals 0 for I up to n. Result times equals whatever goes next to the pi. And so we can also do that with unions or intersections. And so sometimes you'll see, like, if I want to union A1 with A2 with A3 and so on up to n, I can just write that as union from I to n. And you write that AI. I think this is big cup. And I think this is big cap. Don't quote me on that, but I'm pretty sure. So it's basically like, it looks complicated, but it's essentially just a for loop where we have some operation. And so with addition and multiplication, it's easy to write like plus equals or times equals. We don't really have a coding way of representing like union equals, but you kind of get the idea where we take each set as it comes and we union it into this bigger result that we're getting. And same for intersection. Like we intersect each new set that comes in with our bigger intersection set that we're building. Or maybe smaller, because intersection like reduces it. So that's notation. Then the book goes over Venn diagrams, which we kind of talked about. And I will leave you with this fun, interesting problem. Some things about Venn diagrams is like, let's say I've got A, B, and C, and I've got A, B, and C over here. These two are not the same. Why is that? Yeah,
The one on the left, I think A and C share things in common, but not the other one.
exactly. So by drawing one of these, I've made an assumption where you're right. So the one on the left is that C could share some overlap with A. The one on the right says C does not share any overlap with A. So your task to think about as you go home is if I color this in, what's that in set notation? All right, so we're out of time. Thank you for giving me your homework. If you didn't give me your homework, please give me your homework, or drop it in the box outside my office. If you want cookies, I have cookies. I didn't bring them to class because one of the boxes contained peanut butter. I think that's all the announcements, passion presentations. Have a good weekend. Enjoy.